This is the day of the 13th problem. Here we go. Atrium, cubicles. Okay, it's a maze. Negative values. Okay. All right, this seems important. All right. Find the binary representation, count the number of bits that are 1. Okay. And if it's wall, right, so something like y. Shortest route you could take is marked as 0. Fewest number of steps required to reach 31, 39. Okay. Whole input is this. All right, so the algorithm. So you take, say, sum of x times x, 3 times x, 2 times xy, y, and y squared. All right. So you add these together along with the input. Then what? And then you need to do sort of like integer toString of this number here in base 2. Filter on, is it the character 1? And then count this. So count, and then if it's a wall, then it's the case. So it's odd. All right. Thus reaching minimum number of steps. Okay, so I guess, let's see. So if we take the range 4x here, y in here, maybe like this, then nope, not like that. This, and then we basically say if wall xy, then emit here, otherwise here. That. Like we can apply a string to this, interpose new line here, and then print the whole thing. We have to apply str. Yeah. All right. So the maze starts out looking like this. Okay. All right, now how do you find the shortest path through a maze? Okay. We could try to repurpose our breadth first search code. So let's go here. All right, so what we need, so we're going to represent our state as a position. All right. Maze is going to be represented by this structure. enter here. No more strings. Okay. And then the valid moves in a state xy is going to be, let's see, for x value in, let's see, so we need all of the, like this, so we'll call this dx y. So can you only go orthogonally? Taking your current location, yeah, you can't go by diagonals. So in that case, then we can just say, I don't know, like this, and you can either go 1, 0, -1, 0, or 0, 1, 0, -1. Okay. Then we want to say when not wall hump at not quite like that. Oh no, we can just say that. Yeah. Not wall hump plus so up here, say let x be min the max 0, add x dx. Similarly for y, y not wall x this. So not using this maze structure, that's too bad. No, where did I close this wrong? Close the let, close the when, then we'll emit just xy like this. Okay. Then use this whole thing. Able to find fry. Yep. Okay. Able to find final, right? So a state is final when we need to get to 31, 39. Okay. Get rid of this code we don't need. Now, I think we can say breadth-first search starting at 0 or 0, 0, 0, 0, I believe. What is it telling me? I think it's saying that at any given point, there's only 2 places where we can go. Or that our that our edge set is 2, so we can only go down 2 routes at any given point. Is that what that's saying? Let's see if it goes any faster if I take this out. And then we might need to use our heuristic here. So let's grab that heuristic code. heuristic. Let's see, so the heuristic, we'll say it's just for position x, y. We'll just add together however far we are from 31 on x and 39 on y. And then we no longer do that. So I guess what we could also do, yeah, I think it might be a good idea to look at the larger map, or the larger maze here. I can supply. Okay. Let's look at this actual structure here. So, this is supposed to be, all right, so where does it actually start? Starting from your current location is actually 1, 1. Okay, so that sounds like it matters. All right, so here we are at 1, 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, geez. This doesn't seem like it should take that long to find a path through. All right. What are the valid moves at 1, 1? Let's see if it gets this right. Says you can go to 2, 1, which is wrong. 0, 1. So that's wrong. 1, 2. 1, 2. That's right, and 1, 0. It says you can go anywhere, which is just not right. So how am I not? What about in another place? Is this okay? That seems like it's working a little bit better. Okay, when not wall at this position. So I think what's happening, yeah, I'm not sure. It looks like while XY, review the problem. Valid moves to, rather, what happens if final, so let's take this heuristic stuff out for now. My final state is this. Let's see if it actually finds the path here. It isn't. All right. For some reason it's saying that none of these are final. If I take the keys in the map, some final, any of these? No, it can't get there. All right. My guess is that it can't get there because it thinks there's a wall there. In fact, that sounds like a good test to make. A wall. So, no, there isn't. Well, then why can't it? How in the world? Why can't it get there? If it's telling me that the vector 7, 4 doesn't exist. What is it? It shouldn't be looking at any states that it's already been to. Put this back in. This is just okay. All right. Zero edge of zero. That's understandable. That's saying that it's stuck. That's saying it can't. It's these are the only places that it knows how to get. It's saying it's filled up the map. Okay. Huh. If we look at the map, it doesn't seem like that's the case. Seems like it should be able to keep going. What if I sort these keys? Where is it saying that it can get to? 0, 0, 0, 1. So here knows how to get here. And so it knows how to get, okay. 1, 1, 1, 2, 1, 3, 1, 4. Should I draw it, maybe? Okay. All right, so it is making its way through the map. I think it's just, why is it getting stuck? Hmm. Hmm. It's getting out to 70 of these. Is it because I need backtracking? That doesn't sound right. Saying that it's explored 70 nodes. Does that look right? Yes. And does it look like it matches out to the maze? Yes. Wait a minute. This doesn't look right. It shouldn't have been able to get down here. All right, my guess is that valid moves is wrong somehow. Okay, the valid moves are take the difference of, and then go up by this. Okay, got it. Okay. Redefine final to be x31, y39, 92 moves. 88. All right. How many locations, including your starting location, can you reach in at most 50 steps? I think this is it. Let's see. So we start with a state thing of 1. So when we take, so it's 0, we've taken 0 steps and reached 1 state. Here we've taken 50 steps and reached 124 states. All right. Okay. Gained a little bit of a jump on everyone because it had this verbose output here. All right, let's go over the problem. Oh, actually, first of all, let's see. So yesterday I was in danger of falling off. Today I'm a solid 80th place. Cool. Okay. Let's go to the problem. All right. So this is a problem of 2 steps basically. One is how are you going to draw the maze, and or how are you going to generate and represent the maze, and then the other is what is your fastest way to get to a coordinate. So fastest way of getting to a coordinate, that's going to be just an application of the breadth first search that we wrote. Was it 2 days ago? Yeah, that we wrote 2 days ago. And the finding the maze is just applying a predicate to a 2-dimensional space. So what does that look like? So I guess that this polynomial here is some kind of maze polynomial. It must have a certain nice property that maybe there's always a path through it or something. So we have an input which sort of acts like a salt here, and then this system is pretty easy to pretty easy to represent. Let's see. So I guess, yeah. So yeah, in Clojure here, we're just taking the sum, turn it into binary representation here, look for the ones in there, count them, and if they're odd, then there's a wall there. Then I define this maze data structure, which I used a couple times. It turned out to be pretty useful, even though it's not. I don't have to apply it to the problem directly. And the main reason that I don't is that, so once I had generated this, I noticed that when I was sort of enumerating my valid moves in a given state, that I could just call the wall predicate directly rather than trying to look something up in the data structure. If the map was huge, then I guess I'm still not sure. Yeah, whether it's faster, whether it would be faster to call wall and recompute, or to generate a lazy data structure here and just call into it. Anyway, so my implementation of valid moves was unfortunately buggy the first time that I did it, which is that so I wanted to relet here. I wanted to relet X and Y here because I didn't want to have to repeat myself in checking for a wall and then also emitting the pair XY. But what I ended up doing was adding dx and dy in here, and then this was the bug. So here I'm properly emitting the future coordinates, but what I'm basically looking at is, like, if you want to go to the left, then look to see whether there's an open space beyond that wall. So so that was my implementation of valid moves. And yeah, once I fixed that, then the whole thing fell into place, because our breadth first search was just the same that we wrote 2 days ago. And my so both of these debug statements were pretty useful here, because so def m, so this is basically just giving us some visibility into what the state of the search is. And I was able to pretty quickly sort of retrofit this maze definition to include the O's where it had been searched. And yeah, if you look at this, then you can, well, there are a few things that you can check. One thing that you can check is whether the O's are going any place where there's a wall. And I think we can, well, can we find? Yeah, we probably can find spots where that's the case. But what I noticed right here was basically this. So this sort of behavior, and I guess you can see here, like it jumps like it added diagonal. So, but basically this tells me that where to look for the bug, and the verbose output was telling me that that it had run out of edges to search. So yeah, those two things were both helpful. And then, so yeah, then once I fixed the valid move generator, then the algorithm ran super fast and gave me this nice output here, so that when part 2 came around and it said how many places can you reach in 50 steps, I didn't even have to run the program again. I could just look at this output. So that was pretty nice. Yeah, I don't think that I've ever. I think this is probably my first night where I didn't have to write any new code to solve part 2. So yeah, took me a second to make sure I didn't have an off by 1 mistake, but this is basically saying, yeah, at step n equals 0, so 0 steps, you can reach 1 state, which is true. So that's your starting state. Then here we go. This is saying, after 1 step, you can reach three states, and it's pretty nice. So we just jump down here to 50 where it's reporting and give us the right answer. All right, let's look at our Advent calendar here. Yesterday we got the train, and today we're getting, I don't know what this is going to be. But if you want to find out along with me, then tune in tomorrow when we'll be doing day 14. And that's it. Thanks for watching.